Imagine a place where light itself gets lost. A place where the clock slows down and eventually stops entirely. You are looking at the darkest mystery in the universe. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward, and gravity wins so completely, so suddenly, that even the outer layers fall straight in. No explosion, no bright farewell, just a sudden disappearance. In that exact moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Astronomers have even observed stars that seemed stable suddenly vanish from view, as if the light simply blinked out. These are what scientists call failed supernovae. There is no explosion, no fading glow, just an overwhelming darkness. These sudden disappearances suggest a collapse so complete that almost all of the energy is swallowed entirely. It is a stark reminder that not all cosmic deaths make noise. Some happen in absolute silence, buried deep inside gravity's inescapable grip. But the real horror begins here. When a massive star collapses, it leaves behind an abyss. Gravity does not just pull on matter, it bends space and time. The stronger the gravitational field, the slower time flows relative to areas of weaker gravity. As you approach this invisible boundary, the universe changes. If you were to orbit just outside the event horizon of a black hole, time for you would pass much more slowly than for someone far away. Minutes near the black hole could mean years elsewhere. This is not science fiction. It is a real, measured effect called gravitational time dilation. Around black holes, this effect becomes profound. They do not just trap light, they stretch time itself. A black hole does not just trap matter, it warps space-time into a funnel, narrow, steep, and strictly one way. Inside, all paths lead toward the center, toward the singularity. The closer you get, the more time and space seem to trade places, with inward becoming a direction in time, not space. You cannot go back. This twisting of space-time is more than metaphor. Its geometry is drawn by gravity, written directly into the fabric of reality itself. Scientists discovered something even stranger. These monsters do not just exist as isolated graves of dead stars. They lurk at the very center of galaxies, controlling the fate of billions of suns. At the very center of our own Milky Way lies an enormous black hole, a singular point of gravity called Sagittarius A star. It is more than 4 million times the mass of the Sun, yet it occupies a space smaller than the orbit of Mercury. We cannot see it directly, but we have watched nearby stars whip around it at tremendous speeds, tracing invisible loops through the void. Sometimes gas and dust fall inward and flare with X-rays as they spiral into the event horizon. For now, Sagittarius A star sleeps, but long ago it may have burned like a quasar, lighting up the galaxy from within. Today, it is the silent conductor of the Milky Way's heart, pulling stars into a slow, relentless dance. And this is where physics starts to break. When these supermassive black holes awaken, they become the most terrifying engines in the cosmos. At the heart of many galaxies lies a supermassive black hole. And sometimes, as matter falls toward it, not all of that matter disappears. Some of it gets caught in twisting magnetic fields and blasted outward in narrow, powerful jets. These are streams of plasma moving near the speed of light.
These violent jets can stretch far beyond the host galaxy itself, reaching lengths of millions of light years. Galaxies like these are called radio galaxies, and their jets are among the largest structures in the universe. It is a strange, chilling irony. The most powerful outflows in the entire universe come from the very regions around black holes where light can barely escape. Even absolute silence, it seems, can leave a massive scar across the cosmos. When astronomers first looked deep into the universe, they found objects that looked like faint point-like stars, but their light did not behave the way it should.
It took years to realize that these were not stars at all, but distant galaxies with incredibly active centers. A quasar is powered by a supermassive black hole surrounded by a swirling disk of hot, infalling gas. That gas heats up and glows with unbelievable intensity, sometimes outshining the rest of the entire galaxy combined. The first quasars were so far away that their light had traveled billions of years to reach us, yet they looked like tiny, innocent stars in our night sky. A case of cosmic mistaken identity that turned out to be one of the brightest and deadliest discoveries in astronomy. But what lies beyond that boundary? No one truly knows. Not all black holes sit obediently in the centers of galaxies. Some roam. A black hole can be ejected from its birthplace by violent gravitational interactions, kicked out of a galaxy during a massive collision, or flung away by the recoil of a merger.
Once released, it becomes a rogue object, moving silently through interstellar or even intergalactic space. These wandering black holes are incredibly hard to detect. They emit no light unless they pass through gas or pull on nearby stars. But they are likely out there right now, drifting through darkness, unseen and unbound. They carry no orbit, no companion, no home, just mass, motion, and the deep gravity of a thing that fell inward and never stopped falling. When two black holes merge, the violent event sends out a burst of gravitational waves. But those waves are not always symmetrical. If the merger sends more energy in one direction, it can give the new black hole a kind of recoil, a gravitational kick, strong enough to hurl it away at thousands of kilometers per second. Some black holes may be flung entirely out of their galaxies, doomed to drift through the freezing void of intergalactic space forever. Others settle into wide, wandering orbits. These kicked black holes are hard to spot, but astronomers believe they exist. Silent travelers, pushed by the memory of their own violent collision.
Even the heaviest, most anchored things in the universe can be moved by the right kind of wave. But the real horror begins here. Black holes do not just destroy stars, they collide with each other in cosmic dances of unimaginable violence. When two black holes orbit one another, they emit ripples in space-time called gravitational waves. As energy leaks away, the black holes spiral inward until they merge in a final dramatic moment, two invisible giants becoming one. These collisions do not make light, but they send out bursts of gravitational waves that we can now detect on Earth. These gravitational waves stretch and squeeze space as they pass, moving outward in all directions, traveling at the exact speed of light. In 2015, a small satellite named LIGO detected a faint ripple in space-time from more than 1 billion light-years away. It was caused by two black holes colliding, sending gravitational waves across the cosmos. When these waves reach Earth, they stretch and squeeze space by less than the width of a proton. A single chirp from the merger of invisible giants, caught by a tiny detector on a quiet corner of a small blue planet. These black hole mergers happen quietly, invisibly, but with incredible force, converting entire solar masses of energy into waves that ripple across the universe. And for a brief fraction of a second, the fabric of space itself sings.
scientists discovered something even stranger. We assume black holes are the endpoints of dying stars, but what if they were there from the very beginning? Most black holes form from the collapse of massive stars, but there is another terrifying possibility. Black holes that formed in the earliest moments of the universe, before stars even existed. These are called primordial black holes. They may have formed from tiny fluctuations in the dense, hot conditions just after the Big Bang, regions where gravity pulled matter together into ultra-compact knots. Some of these black holes could be incredibly small, while others might have grown massive over time. We have never directly detected one, but if they exist, they could help explain dark matter, seed the formation of galaxies, or unlock new insights into the early universe. They would be older than stars, older than galaxies.
Silent fossils of the first seconds after time began. And this is where physics starts to break. We are taught that nothing can escape a black hole, not even light. But empty space is never truly empty. According to quantum physics, what we call a vacuum is actually a restless sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. This happens all the time, everywhere, creating a hidden hum of creation and disappearance. But when this happens at the very edge of a black hole's event horizon, reality fractures. These virtual particle pairs occasionally result in one particle escaping while the other falls in. The escaping particle becomes real, carrying away a tiny bit of energy lost from the black hole. This process is known as Hawking radiation. Over incredibly long timescales, this slow leakage can cause the black hole to shrink and eventually evaporate completely. For a black hole the mass of the sun, that process would take more than 1 trillion years. It is the quietest kind of ending. Not an explosion, but a long, slow fade into absolutely nothing. But what lies beyond that boundary? No one truly knows. If a black hole slowly evaporates into nothing, what happens to the things it swallowed? What happens to the information? This paradox has forced science to question the very nature of reality. Some physicists have seriously explored the idea that our three-dimensional universe might be a projection from a deeper two-dimensional reality. This is known as the holographic principle. It comes directly from the study of black holes, where information about everything that falls in seems to be encoded on the surface, not the volume of the black hole itself. Some theories suggest that the universe as a whole might work the exact same way. What we perceive as space and depth could be a kind of mathematical illusion, arising from information encoded on a distant boundary.
We look at a black hole and see a void, but we may actually be looking at the edge of reality itself, a stark reminder that even at its most solid, the universe may not be quite what it seems. We walk the earth, feeling grounded, feeling permanent. Yet if you travel far enough from stars, planets, and galaxies into deep intergalactic space, you will find yourself surrounded by what seems like pure emptiness. The temperature there drops to just a few degrees above absolute zero, about 2.7 Kelvin. That is colder than any natural place on Earth, and colder than most environments we can create in advanced laboratories. There is nothing to hold heat, just a scattering of stray atoms and the faint microwave glow of the early universe. These intergalactic voids are the quietest, loneliest places we know, enormous and empty, stretched across millions of light years. They are the universe's deepest shadows. And somewhere out there, wandering black holes glide silently through that freezing dark.
We look up at the night sky and see a universe glowing with light. But most of the matter in the cosmos does not shine. It does not emit or reflect light.
Dark matter is everywhere, shaping the structure of the universe. It is a quiet, invisible framework holding everything else in place. Galaxies follow filaments of this invisible matter, stretching across space. In between lie great voids, nearly empty regions where very little matter exists. And feeding on this web, pulling it apart and dragging it into the dark, are the black holes. Trillions of years from now, the universe will look very different. Galaxies will have drifted apart so far that each one will seem alone in the dark. New stars will stop forming. Old stars will burn out. Even the faint glow of white dwarfs will fade. What remains will be cold, scattered remnants and black holes. Over unimaginably long timescales, even the black holes will evaporate. Matter itself may decay. Eventually, all that remains will be particles, moving through empty space, silent, slow, and alone. This future is called the heat death of the universe. It is not a sudden end, but a vast, dark stillness, a cosmic ocean with no waves, no wind, and no shore. We are living in a temporary universe, a universe that whispers itself into being and eventually whispers itself away. Black holes are not just dead stars. They are the final mechanisms of time. They are the ticking clocks counting down the cosmic eras. They crush light. They stretch time. They wander the dark, unseen. They are the ultimate, inescapable fate of everything that burns. The universe is far stranger and darker than we ever imagined.